Find all real numbers x, y, z greater than or equal to 1, satisfying that the minimum of square root of x plus xyz, y plus xyz, and z plus xyz is equal to the square root of x minus 1 plus the square root of y minus 1 plus the square root of z minus 1. So how can we get started on this problem? Well, we want to somehow incorporate this x, y, and z greater than or equal to 1 condition, which is kind of naturally incorporated into these square roots here. And about these square roots, we want to square both sides, but doing so will make even more square roots, and that will become even messier. So let's just get rid of the square roots entirely. So in particular, we can just let this be a, this be b, and this be c. And solving for x, y, and z gives x equals 1 plus a squared, y is equal to 1 plus b squared, and z is equal to 1 plus c squared. All right, so now we have to figure out what the left-hand side is equal to. This will clearly be a lot more complicated than the right-hand side, which is just a plus b plus c. And since we're looking at a minimum, we can assume without loss of generality that x is a minimum, because then we can permute our solutions. So we have that a is less than or equal to b is less than or equal to c. And since square roots are positive, each of these guys is greater than or equal to 0. All right, so now we can get to work. We have that square root x plus xyz is equal to root x minus 1 plus root y minus 1 plus root z minus 1. And we plug in each of our values here, and we get square root of 1 plus a squared plus 1 plus a squared times 1 plus b squared times 1 plus c squared is equal to a plus b plus c. Now we can square both sides because we have only one square root, and all the square roots vanish from the problem. So we have 1 plus a squared plus 1 plus a squared times 1 plus b squared times 1 plus c squared is equal to a plus b plus c squared. And we want to find a nice way to factor this or do something with this. So let's expand everything out. Doing so gives 1 plus a squared plus, then this guy becomes 1 because that's the constant coefficient. So that's 1. Then we have a squared because it can go here, then here, then here. So that's a squared. Then we similarly get b squared plus c squared. And then we also get the similar terms a squared b squared plus b squared c squared plus c squared a squared. And then finally the term a squared b squared c squared. And this is equal to a squared plus b squared plus c squared plus 2ab plus 2bc plus 2ca. All right, so now that we have this, we can see that these guys cancel out. And what is left after bringing everything to one side is a squared b squared plus b squared c squared plus c squared a squared plus a squared b squared c squared plus a squared minus 2ab minus 2bc minus 2ca plus 2 is equal to 0. And we have a lot of squares here, and it's only a quadratic in a. And a seems like the more restricted one because we have that extra term, and a is the smallest one. So let's write this as a quadratic in a. So this is a squared. Gathering the terms, we have a b squared term, a c squared term over here, and then we have a b squared term here, and then finally an a squared term here. And now we have the a terms. So we just have a and then 2b plus 2c because we have a 2ab and 2ca. And finally, we have the constant terms. So we have b squared c squared minus 2bc plus 2. This is all equal to 0. And this is our quadratic in A. Now, since this is a USAMO problem, and it would be very weird if this quadratic had roots for infinitely many values of B and C, or on that matter, a very large solution set, it would be very hard to classify these solutions. So we are hoping that a lot of the time this quadratic here has no solutions, or in the worst case, one solution. Because if it had one solution, then we could get the unique value for A and solve it from there. All right, so let's find the discriminant of this quadratic equation. So we use the b squared minus 4ac formula, but instead we're not using a, b, and c. We're instead squaring 2b plus 2c, then subtracting 4 times b squared plus c squared plus b squared c squared plus 1, and then b squared c squared minus 2bc plus 2. And we want to show that this is less than or equal to 0. And we can divide both sides by 4 and neatly factor each of these guys here because they can be factored, except when we add 1, subtract 1, it could be factored. In doing so, we get b plus c squared. Remember, we divide everything by 4, minus 1 plus b squared, 1 plus c squared, and then finally bc minus 1 squared plus 1 is less than or equal to 0. And we're factoring things so that we can smartly expand things out. And we can move everything to the other side because we have a lot of squares here. And hopefully we can write things as a sum of squares. Because sums of squares are always non-negative, and when they are 0, all the squares in it must be 0. So if we could write this entire thing as a sum of squares when we move it to the right-hand side, we are set. So let's go ahead and do that. So we negate this by doing this and then making this greater than or equal to 0. Then this is negative b squared plus 2bc plus c squared. And then we can now expand this because it's not too weird. So we have 1 plus b squared plus c squared plus b squared c squared plus b squared or bc minus 1 squared plus b squared bc minus 1 squared plus c squared bc c minus 1 squared plus b squared c squared bc minus 1 squared. And we want this to be greater than or equal to 0. Well, now this b squared and c squared cancel out with these ones over here. And what is left is we have all these square terms, and then we have these terms that are not inside anything. We have a sum of squares plus b squared c squared minus 2bc plus 1 is greater than or equal to 0. This is what we want to prove. But at this point, we notice that this guy here is itself bc minus 1 squared. And this is greater than or equal to 0. And this implies that this quadratic here has at most one solution. And it only has a solution when equality holds in all cases. And all the other squares inside our sum of squares has this bc minus 1 squared term. And we already have a bc minus 1 squared term on its own. So therefore, there exists exactly one solution if and only if bc is equal to 1. Now we can just finish up the problem from here. So let's let b is equal to t, so that c is equal to 1 over t. Then we have that this one here is just 1 plus t squared, and then 1 plus 1 over t squared, and that is equal to t plus 1 over t squared, because we have 1 plus t squared on the top and t squared on the bottom. And that's the leading coefficient of our quadratic, which is over here, because that's how it factors. And so we have a squared times t plus 1 over t squared minus a, then we have 2t plus 1 over plus 2 over t, plus then over here we have bc minus 1 all squared plus 1, which is just this thing over here. And we plug in bc is equal to 1 to get that this constant term is just 1. And this is equal to 0. Now, since this is a quadratic equation with exactly one real root, this should factorize as a perfect square. And indeed it does, because it's just a times t plus 1 over t minus 1 all squared is equal to 0. Therefore, solving for a, we get a is equal to 1 over t plus 1 over t is equal to t over t squared plus 1. And then we also have b is equal to t as before, and c is equal to 1 over t. And now we can finish up the problem by plugging in the values for x, y, and z in terms of a, b, and c. So x is equal to 1 plus a squared, which is 1 plus t squared over t squared plus 1 squared. Y is equal to 1 plus b squared is 1 plus t squared. And z is equal to 1 plus c squared is equal to 1 plus 1 over t squared. And now we have everything in terms of only t squared. So we can just let s equal t squared, since we're assuming that t is greater than 0 as b is greater than 0 or equal to 0. And we get that x is equal to 1 plus s over s plus 1 squared, which is equal to s squared plus 3s plus 1 over s squared plus 2s plus 1. And y is equal to 1 plus s, z is equal to 1 plus 1 over s. And this is our solution set. For all s greater than or equal to 0, we have the following solutions, or x greater than 0, because 1 over s is then not defined. We have x, y, z is equal to s squared plus 3s plus 1 over s squared plus 2s plus 1, then 1 plus s, and then 1 plus 1 over s. And as before, since we're assuming that x was a minimum, we have to permute these solutions. So we can just write and permutations. And this is a complete solution set to our USAMO problem, where we have that the minimum of the square root of x plus xyz plus and the square root of y plus xyz and the square root of z plus xyz is equal to the square root of x minus 1 plus the square root of y minus 1 plus the square root of z minus 1. We solve this by getting rid of all the square roots using suitable substitutions, writing everything as a quadratic, and realizing that the discriminant is negative of a sum of squares. And that finishes the problem. So thank you so much for watching this video. Please subscribe if you'd like to see more.